If you're here, you probably want to build a really good AI agent, but most advice out there will tell you to start by just building one. That's exactly the reason so many projects fail, and it's easy to see why. This year has been nothing but hype. Agents everywhere. Every post, every headline, every demo. And yes, in the right context, agents can be incredible. But the truth is, most real-world systems don't need them. In every production AI system I've built, the biggest wins came from single modular workflow patterns, not autonomous agents. So in this video, I'll break down the 5 workflow patterns that actually work and show you exactly when an agent makes sense. By the way, if you're new here, I'm Fraser Dorado. I've spent nearly a decade building large-scale enterprise systems, and now through my AI and automation agency, I help businesses design scalable and reliable solutions that solve real-world problems. I share those same frameworks and lessons here so you can apply them in your own work. With that, let's first start by defining what we actually mean when we say AI agent. At its core, an agent is just a loop. It observes the world, decides what to do next, and acts, usually powered by a large language model. Sounds impressive, right? A system that plans its own actions, reasons through problems, and maybe even calls APIs all on its own. That's why the idea exploded this year. It feels like the natural next step after chatbots, and it made everyone chase the dream of an AI that can run itself. But here's the problem. When you try to apply that loop directly to a real business process, it almost immediately falls apart. You get unpredictable outputs, broken task flows, and endless retries. The same prompt that worked yesterday fails today. The issue isn't that the models are unpredictable, that's by design, since they're generative. It's that the systems around them lack structure. Logic, state, and control flow end up buried inside prompts instead of being modeled in code, which makes scaling and debugging a nightmare. The truth is, agents aren't bad tech. They're just the wrong starting point. And most teams jump straight to autonomy before they've mapped out the flows and nailed the structure. That's where workflows come in. Structured patterns that turn generative models into dependable systems. Think of it as a system where LLMs and tools are orchestrated through predefined code paths, not through open-ended reasoning loops. Now, whether it's a simple workflow or a full-blown agent, it all starts with the same core foundation, an augmented LLM, a language model enhanced with retrieval, tools, or memory. Workflows build on that foundation by adding structure. They define how each model call, tool, or data source connects and when each should run. In almost every production system I've helped design, the most reliable setups all follow one of a few recurring workflow patterns. These aren't new inventions. They're proven software engineering concepts just adapted to AI. There are 5 core patterns worth knowing: prompt chaining, routing, parallelization, orchestrator worker, and evaluator optimizer. Let's start with the simplest one, prompt chaining. Prompt chaining breaks a larger task into a sequence of smaller steps, where each LLM call processes the output of the previous one. Think of it like a production line, where each step does one clear job before handing its result to the next one. The main trade-off here is latency for accuracy. You add a few extra model calls, but each call becomes simpler and more reliable. You can also add programmatic gates between steps, checks that make sure intermediate results are valid before continuing. That's how you catch issues early and keep the flow on track. So when do you use this workflow? Either when the task can be clearly decomposed into predictable subtasks, or when you need deterministic control over what happens at each stage. For example, generating a blog post using AI. You first outline the document, validate it against specific criteria, and then expand it into a full draft. Let's quickly look at how prompt chaining would be implemented. In this example, I've built a simple workflow to generate articles on a given topic. It starts with the research step, where it gathers information, so we pass in the user prompt and the system prompt to the LLM, followed by the writing step, where we give it the topic and the results from the research step. Again, make an LLM call with that information, and then finally pass those results to a summary step, where it summarizes the entire content. As you can see here, I've created a simple chain where I'm calling each function sequentially, and then I'm logging the output. Let's run this. Awesome. Once it's done, you can see the result like this, right? Where you have the step 1 where it does a research on the topic of basic overview of generative AI. It writes the content and then creates a summary. And here's the output from each step. It creates an overview along with the details. It creates the final content. And then the key takeaways. Prompt chaining is the foundation of everything else. But what if your inputs aren't all the same type, or the right next step depends on the content? That's where routing comes in, a workflow that helps your system make decisions. Routing classifies an input and directs it to the right follow-up task, prompt, or model. Think of it as traffic control for your AI systems, deciding which path a request should take. This workflow gives you a separation of concerns. Instead of one generic prompt trying to handle every type of input, you build smaller, specialized prompts that excel at their specific job. Without routing, optimizing for one kind of input often hurts performance on others. So when do you use this workflow? Either when your application has distinct categories of tasks that need to be handled differently, or when you can reliably classify which category an input belongs to, either with an LLM or a traditional classifier. A good real-world example of this would be directing different types of customer queries, like general questions, refund requests, or technical support, into separate downstream processes. Let's look at a quick example of how routing could be implemented. In this example, I've created a routing workflow for customer support tickets. As you can see here, I've created a support handler, which is inherited by the technical handler, which handles technical support issues, followed by the billing handler, which handles billing and payment issues, and the general handler, which handles general inquiries and feedback. I've also created a response formatter to synthesize the final response, and a support router, which consists of two classes. One is classify, which classifies the user query to the right category, and route, which then takes the classified message and then routes it to the correct workflow. To see this in action, I've created a few example tickets, a technical ticket, a billing ticket, and a general ticket. Let's run this. As you can see here, the first message is classified as technical, and it's been delegated to the technical workflow. And then you get a final response, which I think is pretty cool. And moving on from there, you get the second message, which is then classified as a billing issue, because as you can see, it's about being charged twice for a subscription. And then you get a result like this. And the last message is a general inquiry, which has been classified as a general inquiry, and then you get a formatted message just like this. Routing adds flexibility and keeps your logic explicit. But what if you need to handle many pieces of work at the same time? That's where parallelization comes in, a workflow for running multiple model calls at the same time. Parallelization shows up in two main forms, sectioning and voting. Sectioning means breaking a task into smaller independent parts that can be run in parallel. And voting means running the same task multiple times or with different prompts and then comparing or aggregating the results for higher confidence. Think of it as the difference between dividing the work and double-checking it. So when should you use this workflow? Either when the task can be independently parallelized for speed or scale, or when you want multiple perspectives or attempts to improve accuracy and reliability. A good real-world example of sectioning is running multiple LLM instances where one handles user requests while another screens for inappropriate content. And an example of voting is running multiple model prompts to review the same piece of code for vulnerabilities and then merging the flag results. Let's look at a quick example of how parallelization might be implemented. In this example, I've created a simple workflow that takes a blog and generates posts for different social media platforms. As you can see, there's a sample blog post here. And then I've created a few platform generators. So a LinkedIn generator, a Twitter generator, and an email generator. And I've run these both sequentially and in parallel so that we can compare the results. And I've logged the outputs. So let's see this in action. It's now generating the content in sequence. Great, it's done with that, and it's now generating the content in parallel. Awesome, it's done with that, and now it's executing it in async. Great, so it's done. As you can see here, running it in parallel is a lot faster. Usually running in parallel and using async pattern is almost the same, but because I have background processes right now, it's varying, but it's a lot faster than running it sequentially. Parallelization helps you scale and cross-check your systems, but sometimes you can't define all the subtasks ahead of time. You need something more dynamic, something that can decide what to do next based on the problem itself. That's where the orchestrator worker pattern comes in, a workflow designed for more dynamic, unpredictable tasks. In the setup, a central orchestrator coordinates the work. It breaks down the main task into smaller subtasks, delegates them to worker models or functions, and then combines the results into a final output. Think of it like a project manager, assigning tasks to a team. Each worker specializes in one thing, and the orchestrator makes sure everything stays aligned. This workflow shines when you can't predefine every subtask in advance. For example, in coding, the number of files that need to be updated and what kind of changes each require will depend on the specific request. So when should you use this workflow? When the tasks are complex or open-ended and the exact subtasks vary per request, or when you need dynamic coordination between specialized models or tools. A good real-world example of this would be a coding agent that makes coordinated edits across multiple files, or a research assistant that searches, filters, and synthesizes data from multiple sources. Let's now look at how an orchestrator worker workflow might be implemented. In this example, I've created an orchestrator workflow with multiple researchers. As you can see here, there's a background researcher, trends researcher, a challenges researcher, and a general researcher. And all of this is combined in the research orchestrator, where the worker nodes are mapped, and it has a planning step where it decides what needs to be done. It then executes it and synthesizes a response. Let's look at this in action. I've given it a topic of coffee culture around the world. It's now doing the planning, and it's decided what tasks need to be executed. So it's going to do a background search, a trends, and then challenges. As you can see here, it's already done with the researching the background. It did a web search for analyzing the trends, and now it's trying to identify the challenges. And now it's synthesizing the final report. And just like that, we have our entire research complete. The orchestrator worker pattern gives you flexibility and coordination, but sometimes even that isn't enough. What if your system could not only coordinate tasks, but also evaluate and improve its own outputs with every iteration? That's where the evaluator optimizer pattern comes in. This is where your system starts to improve itself through structured feedback. In this workflow, one LLM, the optimizer, generates an output while another, the evaluator, reviews the output and provides feedback or a score. The optimizer then revises its response based on the evaluation, closing the loop. Think of it like an automated peer review process. One model writes, another critiques, and together they converge on a better result. So when should you use this workflow? When you have a clear evaluation criteria that can be expressed as rules, rubrics, or structured prompts, or when iterative refinement measurably improves output quality. A good real-world example of this would be research or search tasks that require multiple rounds of analysis where the evaluator decides whether more iterations are needed. Let's look at a quick example of how the evaluator prompt loop might be implemented. In this example, I've created a recipe generator in which the recipe should abide by a specific set of constraints, as you can see here. For example, it should have at least 30 grams of protein and 15 grams of carbs and few other requirements. And I've created 3 classes. One is the recipe generator that actually generates the recipe. One is the recipe evaluator that takes in the generated recipe and evaluates it against specific criteria that we have mentioned, as you can see here. And then we have the recipe optimizer that runs the recipe generator and the recipe evaluator in a loop till it's satisfied with the result. Let's see this in action. As you can see, this is the recipe request. And now the recipe optimizer is running the first iteration. It generated the recipe and now it's evaluating the recipe. It wasn't satisfied as the criteria were not all met. And now it's running a second iteration. So it generated the revised recipe and it's evaluating it again. As you can see, again, it did not meet all the requirements. So it's running a third iteration. It's evaluating it again. And now it has met all the criteria and you have the final recipe. Pretty awesome. The evaluator optimizer pattern is powerful because it introduces self-correction. The model learns to refine its own work within guardrails you define. And once you combine this with orchestration and tool use, you're only one step away from agents. Now that we've seen all the patterns, when do we actually use agents? Agents have the ability to plan and act autonomously. They are built on the same foundation, an augmented LLM, but they operate in a loop. Agents shine in open-ended problems, situations where you can't predict how many steps are needed or hard code every path in advance. A good real-world example is a coding agent that edits multiple files based on a single instruction, or customer support flows where the system needs to reason across tools and data sources in real time. But that autonomy comes with trade-offs: higher cost, longer running times, and the potential for compounding errors. That's why in production, agents should always be tested in a controlled environments with strict guardrails and clear stop conditions. The key takeaway here is that agents are not a replacement for workflows, they are the next layer built on top of them. If building an AI agent sounds complicated, I recommend watching my video on how to build an AI agent, where I break down the core logic in a simple, beginner-friendly way. So to bring it all together, most AI systems don't fail because the models are bad. They fail because the systems around them lack structure. Workflow gives you that structure: clear logic, predictable behavior, and a foundation you can trust. Success in the LLM space isn't about building the most sophisticated system, it's about building the right one for your needs. Start simple, evaluate thoroughly, and only move to multi-step or agentic systems when simpler solutions truly fall short. Because at the end of the day, building great AI systems isn't about chasing autonomy, it's about mastering structure and using it to scale your AI capabilities reliably. And when you're ready to take the next step into agents, you'll have the foundation to do it right. If you want more deep dives on building AI systems, hit subscribe so you don't miss the next one.